So here I provide solutions to exam number 2. The two exams were slightly different, especially on the first page. The difference didn't make it any more difficult or any easier. It just was to change some of the answers. Most of you did, reasonably well on this test. Our average went up from the first exam. So good. But they're probably we had problems that we wondered about. If you look in the panel where this video was posted, I've put the times of the problem number. So if you want to look at number 4, and you feel good about the first 3, and you just want to look at number 4, then you can find the time in the video where that problem starts. And then in this video, I'll just work through all of them. I won't work them all the way, but I'll at least identify the enough to get to where we could solve the problem. We could finish it, no problem. All right, so the first one is a pretty straightforward, in fact, a very straightforward partial fraction decomposition case 1. I trusted you to factor the denominator. This is the afternoon class. The factors were really the same, same process. And here, x minus 6 times x minus 1. Hopefully you can see that. I wanted to make it pretty straightforward. And now we can see we have two linear different factors. So that's definitely case 1. And so our decomposition pattern is some number over x minus 6 plus some other number over x minus 1. We equate numerators. On the left, 4x minus 3. On the right, a times x minus 1. If we add those fractions up, this would be the numerator. B times x minus 6. You plug in 1 the way that I showed you to do this. Some of you learned a different way, or and there are other ways to get there. I tried to show you what I think is the easiest way. When you plug in 1, I get 1 on the left, and I get minus 5b on the right. And so therefore b is minus 1/5. And then we plug in 6. We get 21 on the left and 5a on the right. And therefore a is 5/21. 21/5. So now we're going to integrate this decomposition, but now we know the values of a and b, so I'll just come down here and write it. I'm going to pull the constant a out, 21/5, and then we get the natural log of x minus 6. Absolute value, x minus 6 can be negative. Minus b, 1/5, the natural log of the absolute value of x minus 1. And if we want to do it, we can write a plus c. So there we go. Problem number 1. Problem 2. So here are 3 integrals. 2 of them are improper. 1 is proper. The one that is proper is the third one. X squared plus 1 is defined everywhere. It cannot be 0, so that's a perfectly normal integral. So that's the one we'll ignore. For the other 2, we write them as limits. And so for the first one, I'm going to get the limit. Of course, the infinity makes it improper. We'll let b slide off to infinity, and we'll integrate from 2 to b. I'm going to write that function as x plus 2 to the minus 3 in anticipation of part C. Maybe when you wrote it, you hadn't looked at part C. That's the first one. Here's the second one. The problem is at 5. X minus 5 is 0. So we're going to it's a lower limit. I like to call it a. It's going to slide into 5 from above so that the radical is defined. And then we'll integrate from a to 9. And again, I'm going to set it up for the antiderivative. Write it to the minus 1/2 power dx. Okay, using correct mathematical notation. And then on part C, you pick one of those. Both of them are just the power rule, raise the power, the limits. The variable part goes to 0 and you're left with the constant. I don't remember the answer. I don't think I need to work through part C. So let me pause this and I'll load new paper. All right, problem 3, we have a rational function, and notice the powers, the degree of the numerator and denominator, both 2. So it is improper. We need a long divide. So we'll take x squared plus x, divide by x squared plus 1. X squared into x squared goes once. Plus 1, subtract, and get x minus 1. That is of degree 1, less than degree 2, what we're dividing by, so we're done. This original antiderivative is equal to the antiderivative of the polynomial piece, which is just the constant 1, plus the proper rational function, x squared plus 1. Okay? Now, you might think, well, this is a case 3, partial fractions, but it really isn't, because the only part of the denominator is x squared plus 1. You can't really decompose it. What we can do is, obviously, we can integrate the 1, we'll get x. And then I can break that into 2 separate integrals. X over x squared plus 1 minus 1 over x squared plus 1. All right, the last guy is inverse tangent, no problems there. And this one, the derivative of the bottom is 2x. I got the x, that's the hard part, but it's there. All I need is a 2. I can get that by canceling it out, and now I have a function on the bottom. Its derivative on the top, the antiderivative of that situation is natural log. X squared plus 1 can't be negative, so no absolute value signs needed. And there we go. Question number 4. One of these is separable, one isn't. Well, the way they're written, neither one looks separable, but if I look closely at the second one, I can pull that x squared out. And fortunately, I have y squared. I have one on both terms, so I can write the derivative as the product of a function of y times a function of x. You can't do that with the first one. So if you're in the morning class, I told you to put an x on the one that is separable. Well, that probably felt weird to you. It wasn't exactly what I had in mind, but you all followed my instructions perfectly. I changed it though, circle the one that is. And so I nearly got it circled already. And then we're going to solve it. So divide by y squared, separate the variables, multiply by dx, x plus 1 dx. Integrate minus 1 over y on the left, 1/2 x squared plus x plus c. Solve for c. Y is equal to 1. So I get minus 1 equals, and I'm plugging in 0. These first 2 terms go away. I get c. And so now I'm at minus 1 over y equals 1/2 x squared plus x minus 1, the constant. And then we just solve for y. We need to negate and reciprocate. So here's the negate. Here's the reciprocate. Some of you were a little careless with your reciprocating and reciprocated term by term. Unfortunately, algebraically, that's not valid. So be careful. There's the right answer. A lot of you got there and stopped. I don't blame you. But we can clean it up a little bit. Notice with the 1/2 here, it's like a compound fraction. So just to make the answer as pretty as it can be, I'm going to absorb the minus sign into the denominator by flipping all of those signs. And then I'm going to multiply by 2, just because I like pretty answers. So I'm going to have 2 on top. And then remember, we're flipping the sign and multiplying by 2. So this 1 over here becomes a 2. we flip the sign, so it's positive, and then I'm going to get minus 2x. Right, you've got to distribute that. We're multiplying top and bottom by 2, but we've got to distribute it on the bottom. And so I get minus x squared. The 2 we're multiplying by cancels the 2 on the 1/2. And I believe that's the right answer. Again, a lot of you have this thing I sort of shakily circled, and I didn't ask you to simplify it. So let me pause again and I'll load page 3. All right, problem number 5, page 3. Using the appropriate trig function, find the antiderivative shown. And in bold, you must use, and italics, must use trig substitution. Any other method will not earn any points. It turns out there's probably an easier way to do this, but I wanted you to show me that you could do trig substitution, and I wanted the eventual work to not be more complicated than it needed to be, and that's why I gave you this particular one. So this is case 2. We're going to replace x with 5 tangent theta. Should be memorized. Most of you did a good job with that. We don't have to think about it. Dx is 5 secant squared theta d theta, and that makes the radical 5 secant theta. So we rewrite the integral in terms of theta. I got an x here in first, that's just 5 tangent theta. And then I have the radical, which is 5 secant theta. And then the dx, which is 5 secant squared theta, d theta. Take all those 5's out, 5 cubed. And then I'm using up my space with this pencil. Let's be efficient here. Notice right here, remember the 5's are gone. Right here, tangent secant is the derivative of secant. So if you let u be secant, then du is just what I said, secant tangent. So this integral is really like, take the 5's out, it's like u squared. Here's u squared, and here's du, tangent, secant, d theta. I didn't want to actually do it. So when I wrote this on the key, I wrote the detail. I'm writing sort of big here, using up my space, so I'm going to be efficient. Hopefully you agree with me. If you make this substitution, this is like u squared du. So just raise the power, divide by the new power. Of course, our u is secant cubed theta. So there's our answer. Unfortunately, it's in terms of theta, but we know theta is the angle whose tangent is x over 5. And we also know we can draw a picture of that angle. Here it is. Opposite over adjacent gets us tangent. And of course, the hypotenuse then is our radical, square root 25 plus x squared. And the secant of that is hypotenuse over adjacent. So we're going to get 5 cubed over 3. And then we're going to cube the secant, which is the square root of 25 plus x squared over 5. So there's the answer. We can pretty it up a little bit. Notice I have a 5 cubed here, and I have a 5 cubed in the denominator. Those are going to go away. And what's left? Well, the 3 is still there, the 1/3. And then I'm going to have, there's a variety of ways to write it, 25 plus x squared to the 1/2 power, the square root, and then we cube it. So maybe we can write it like that. Plus c. Done. Number 6, partial fraction decomposition. Solve. So write the decomposition. I'm asking you to do 2 things. Write it and then solve for the constants. So this function, of course, the case depends upon the factoring. I can take an x cubed out. And so I have a case 2 integral. I have a linear factor x repeated 3 times and another linear factor. So the decomposition is going to go like this. There's the original. And we're going to take a over x plus another constant over x squared plus another one over x cubed plus a fourth one over x minus 2. And then we equate numerators. Well, I use the least common denominator. I get 3x plus 2 on the left, no problem there. Then a is already over one of the x's. He needs the other two, as well as the x minus 2. B is over two of them, needs the third one, and the x minus 2. Minus 2, he said. C is over all of the x's, so just needs the x minus 2. And D needs only the x's, but he needs all of them. So we need to solve for the constants, plug in 0. All of the terms go away except for C. On the left-hand side, we get 2. On the right-hand side, we get minus 2C. So C is minus 1. And then we can plug in 2, make some progress. I get 8 on the left. 3 times 2 is 6 plus 2 more. And then the first 3 terms go away. Plugging in 2, we're multiplying by 0. And then I get 2 cubed, which is 8. So D equals 1. Because we're case 2, what I recommend next is comparing powers. I need to know A and B. All right, so I look closely at A here. I can see that A is going to be a coefficient of the cubes. So let's, and the only other cube is D, which I already know. So that's going to work out just fine. So I have no x cubes on the left. I get A of them out of the first term and none out of the second, none out of the third, but finally D of them. And we know that D is 1, and therefore A is minus 1. Finally, for B, we can pick on squares or first power. Let's pick on squares. I have none on the left. I get minus 2A of them out of the first term, right? X squared times minus 2 times A. And of course, we know the value of A. And then I get B of them out of here. No squares out of this term or the last one. And we know that A is minus 1, so B equals negative 2. Right, we get 2 plus B equals 0. All right. The last problem. Problem number 7. So we're asked to find the area in the first quadrant under a function. Functions were slightly different. Can't draw a very pretty graph with this pen on this iPad. So the function is x e to the minus x squared times a constant. I think the morning class had 8, the afternoon had 10. I'll do 10, doesn't really matter. So you may have been wondering, why is this on the test? Well, because the answer is an improper integral. The area is the integral from 0 to infinity. The first quadrant starts at 0, and this function never quite makes it back to the x-axis. So we integrate up to infinity, 10x e to the minus x squared. And I asked for the area, not an integral. So we got work to do. Of course, this is an improper integral. I think I asked you to use correct mathematical notation. 0 to b. Now, the antiderivative. Some of you made it much more difficult than it is. The derivative of the inside function is minus 2x. I have the x. I can get any constant I want. The constant I want is 2. Well, I got a 2 hiding right there in the 10. I need a negative 2, so I need to adjust the sign. I'm going to split 10 into 5 times 2. Take the 5 out. Make it negative because I need a negative 2x. Actually, talking my way through this here, we just then get the antiderivative is just e to the minus x squared. I'm going to go from 0 to b. So again, what we're doing is we're letting u be the inside function. Making weird equal signs today. So du is minus 2x dx. So just at an antiderivative level, split the 10 into 5 times 2. And then you can see this becomes minus 5 e to the u. And the antiderivative is just e to the u. There it is. And now plug in our limits. E to the minus b squared minus e to the 0, 1. This thing goes to 0. Therefore, the limit is minus 5 times minus 1. I think in the morning class, this 10 was an 8, and you got 4. You had to take the 2 out, which took a 4, and you got 4 for your final answer. All right, there you go. Check it out.